Ever pondered what it would be like to travel back in time or leap into the future? Imagine if time was not just a straight line from the past to the future, but instead a dimension intertwined with the three dimensions of space we're familiar with. This is the concept of space-time, a four-dimensional framework that merges the three dimensions of space with the one dimension of time. Our everyday experience tells us that space and time are separate entities. We move freely in space, but time, it seems, only marches forward. However, the concept of space-time challenges this ordinary perception. Instead of viewing space and time as separate entities, space-time unifies them into a single entity. It's like a cosmic fabric upon which the universe is etched. Think of it this way. Each moment you live through is a slice of this four-dimensional space-time. Your past, your present, your future, they're all there laid out in this cosmic quilt. It's a bit like watching a movie where every frame exists simultaneously, rather than one after another. This concept of space-time is not just a theoretical construct, it's a fundamental part of our understanding of the universe. It's at the heart of Einstein's general theory of relativity, one of the most successful theories in the realm of physics. This theory tells us that space-time isn't a static backdrop against which the universe unfolds, but rather, it's a dynamic entity that can be curved, twisted, and warped by the matter and energy within it. So next time you look at your watch or gaze up at the stars, remember, you're not just moving through space. You're moving through space-time, a four-dimensional framework where space and time are inseparably intertwined. Dive into the fascinating world of space-time, where the lines between past, present, and future blur. You may have heard of Albert Einstein, but do you know how his theory of relativity revolutionized our understanding of space-time? Let's take a moment to dive into this groundbreaking theory. Einstein's special theory of relativity, introduced back in 1905, proposed a rather radical idea. The laws of physics are the same for all observers, regardless of their motion or position. This means that whether you're sitting still in a cafe or zipping past in a high-speed train, the laws of physics remain unchanged. This might sound straightforward, but it was a huge departure from the established Newtonian physics of the time. Einstein didn't stop there, though. A decade later, he introduced his general theory of relativity, an extension of the special theory that included gravity. Here's where things get interesting. The general theory of relativity introduced the concept of space-time, a four-dimensional fabric woven together by the three dimensions of space and the one dimension of time. Think of space-time as a giant cosmic trampoline. Now, if you place a heavy object on the trampoline like a bowling ball, it creates a dip or a warp in the fabric. This is similar to how mass and energy warp and twist the fabric of space-time. The bigger the mass, the bigger the warp. So, a planet like Earth creates a significant warp in space-time, which we experience as gravity. In other words, when you drop an apple, it falls not because there is some invisible force pulling it down, but because it is following the curvature of space-time created by Earth's mass. Einstein's theory also predicted that even light would follow this curvature, a prediction that was later confirmed by observing starlight bending around the sun during a solar eclipse. So, in Einstein's universe, space and time are intertwined in a cosmic dance, choreographed by mass and energy. And this dance, my friends, continues to shape our understanding of the universe and our place within it. What if we told you space-time isn't just a theoretical concept, but a reality we experience every day? Yes, you heard it right. The concept of space-time, as fascinating as it sounds, is not just confined to physics textbooks or scientific laboratories. It's an integral part of our daily lives. Take, for instance, the Global Positioning System, or GPS as we commonly refer to it. This handy tool, which helps us navigate through winding roads and crowded cities, wouldn't be as accurate without accounting for the effects of space-time. To understand this, let's imagine two clocks, one here on Earth and another on a satellite orbiting our planet. You'd think they'd tick away in unison, right? Well, not exactly. According to Einstein's theory of relativity, time ticks slower in stronger gravity. So the clock on Earth, which is in a stronger gravitational field, runs slightly slower than the clock on the satellite. This difference, as minuscule as it is, could cause your GPS to be off by about 6 miles if not accounted for. But the reality of space-time doesn't just stop at our GPS systems. It permeates through the very fabric of our universe. The bending of light around massive objects, the stretching and squeezing of space due to gravitational waves, the mind-boggling phenomenon of black holes, all these are tangible manifestations of space-time at work. So while we go about our daily lives, we're constantly moving within this four-dimensional structure of space-time, witnessing its effects in ways we might not even realize. It's this intricate interplay between space and time that validates Einstein's groundbreaking theory and broadens our understanding of the universe. The next time you look up at the night sky, remember the stars aren't just distant points of light. They're part of a vast cosmic stage where the drama of space-time unfolds, and we, as humble spectators, are given front-row seats to this grand spectacle. Remember, every time you check your GPS, you're experiencing the reality of space-time. Have you ever wondered what the discovery of space-time means for us and our understanding of the universe? Let's delve into the implications of this fascinating concept. The discovery of space-time has dramatically altered our perception of the cosmos, leading to mind-bending phenomena like black holes and time dilation. Let's start with black holes. They are regions in space-time where gravity is so strong that nothing, not even light, can escape. This gravitational pull is so powerful because matter has been squeezed into a tiny space. This can occur when a star is dying. Because of this, black holes are invisible to the naked eye. They are a direct consequence of the warping of space-time predicted by Einstein's theory. Time dilation, on the other hand, is a difference in the elapsed time measured by two observers, due to a relative velocity between them or to a difference in gravitational potential. In simpler terms, time runs slower wherever gravity is strongest. And this is because gravity curves space-time. This phenomenon is not just theoretical, it has been tested and confirmed by numerous experiments. For instance, scientists found that clocks run slower the closer they are to a gravitational source like Earth. Both these phenomena challenge our traditional concepts of space and time. They suggest that space is not a static stage on which events unfold, but rather it's dynamic and constantly influenced by matter and energy. Similarly, time isn't an absolute universal tick-tock that marches forward at the same rate for everyone, everywhere. Rather, it can stretch and squeeze under certain conditions. These implications open up a world of exciting possibilities. They suggest that the universe is far more complex and fascinating than we ever could have imagined. We may even have to rethink some of our fundamental assumptions about reality itself. The discovery of space-time has truly transformed our understanding of the universe, unveiling a realm where the impossible becomes possible. So, how does the concept of space-time and Einstein's theory of relativity fit together? We've journeyed through the enigma of space-time, a four-dimensional fabric woven with the threads of three spatial dimensions and one of time. We've explored Einstein's groundbreaking theory of relativity, which redefined our understanding of gravity, not as a force, but as the bending of space-time by massive objects. The reality of space-time, as we've seen, is not just a mathematical abstraction, but a tangible aspect of our universe, influencing the motion of everything within it. The implications of this understanding are far-reaching, affecting everything from GPS navigation to our perception of the universe. The concept of space-time and Einstein's theory of relativity, then, are not just connected, but intricately intertwined. They form the basis for our modern understanding of the universe, guiding our exploration of its most profound mysteries. In the captivating world of space-time, we find Einstein's theory of relativity at the heart, guiding us through the mysteries of the universe.